So we had just our generic probability distributions. And then we got into one specific type called the binomial distribution, which, remember, to be binomial, it had to only have two possible outcomes, a fixed number of trials, and they were all independent of each other. We are going to now talk about the normal distribution. This is probably the most commonly used one, and we're going to talk about, well, yeah, I'm just going to stop there. Let's look at this. So, the probability density function is just an equation that we can use to find probabilities of continuous variables. This is what's different. If you think about in chapter 6, we talked about regular probability distributions, but it was all discrete data because we could make a table, we could list our x's and their probabilities. We talked about the binomial, but that was discrete. 0, 1, 2, 3, those were our options. So this is the first time we've ever gotten into something for continuous data. Just like everything else though, if we're talking about probabilities, they have to add up to 1. So if we're looking at the graph, the area under the graph is 1. Probabilities always have to be positive. So the height, if we were drawing a graph of the probabilities, it would always have to be between 0 and 1 for each given probability. So the first thing that this section talks about is the uniform probability distribution. We're not going to see this very often, and this section is about the only time we're going to touch on it. But that's essentially a situation where the probability is always the same. So for instance, suppose that the United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So 10 a.m. would be like x equals 0. 10:01 would be when x is 1. 10:02 when x is 2, right? And each one is equally likely. So that is to say your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. So every time interval, every minute has the same probability. So our x could be anything between 0 and 60 because it's the number of minutes that have passed in an hour. Everything has the same probability. That's a uniform distribution. Uniform, all the same. The next slide I put a graph of that. So if it's uniform, because it is continuous data, we don't just have lines because couldn't your package, it doesn't have to arrive at 10:01 on the dot, does it? It could arrive at 10:01 and 5 seconds after that, or 6 seconds after that, and so forth. So it's continuous. We don't just have the vertical lines going up. We have a box here because everything had the same probability. Where did I get this 1/60?
There's a chance.
Yeah, my entire probability has to add up to 1, and my length of time, if we start at 0 and we end at 60, 60 minus 0 is 60. So each place has a probability of 1/60. The area of this, if you did length times width, 60 times 1/60, we get 1, which is what I said on the last one. So we could use this to answer a few questions. Find the probability of choosing a time between 15 and 30 minutes. So we know that the probability is 1/60. If you are between 15 and 30 minutes, how wide is that time interval? 15. So you just take 1/60 times 15, and you get? Yep, 0.25. So there's a 25% chance my package will arrive between 10:15 and 10:30. All right. The next one, I kind of flipped it around on us. there is a 30% chance your package will arrive between the next blank minutes. Okay, I know my probability is 1 out of 60. This time I'm trying to find my number of minutes, but my probability then has to be 30% or 0.3. So if you multiply over your 60, you get 18. So there's a 30% chance that my package will arrive in the next 18 minutes. Any questions so far about the uniform distribution? Like I said, it's not one we're going to spend a lot of time focusing on because it doesn't happen very often that everything has equal probability. I think there's the first homework question is about this, but then we're going to just kind of branch into the other continuous variables. All right. We have drawn histograms before. And relative frequency histograms, that's just when we had like histogram, remember, it's just kind of like those rectangular bars. If you were drawing relative frequency, that's just like your probability of each one. What you need to know is when I talk about the normal curve, our histogram has to be symmetric and bell-shaped. We've talked about symmetric before when we talked about if data was skewed or not. And in order for all this normal stuff to work for us, our data can't be skewed. So the key, when we're talking about normal data, it has to be symmetric and bell-shaped. No skew. So if I look at this, this is just the normal probability distribution. Within this, your center, your highest point, if it's not skewed, that is your mean. We'll talk a little bit about inflection points. There's just going to be a few questions that I give you in this section where we're just going to look at a graph and find the mean and standard deviation from this curve. So that place where our graph kind of flips direction, you know, it's coming down, then kind of starts to flatten out. We call that an inflection point. But what that is, that's kind of where our standard deviation starts to kick in. So for instance, if I gave you, like what I'm going to give you on the homework, something like this. Let's pretend I can draw a good curve. And if I labeled this as 7.5, I said this was, let's go with 9, and this was 6. I could ask you to find the mean and the standard deviation from that. The mean has to be your center, so it would be, okay, standard deviation. That would be from my center out. So how far is it from 7.5 to 9? Is that the same as the distance from 7.5 to 6? Yes. So this particular normal distribution has a mean of 7.5, a standard deviation of 1.5. So if I gave you some graphs, could you pick out that information from them? So there's like 3 of your homework questions right there. Just looking at that curve and identifying them. When we talk about the normal curve, here are all the things that are true about it. It's always symmetric about the mean. Just like we said, the mean is the center. If it's bell-shaped, it's the same on both sides. Because it is symmetric, the mean, median, and mode are all going to be the same value. It's right there at that center. We talked about the inflection points. That's just your measure of where your first standard deviation hits. Just like any other probability, area under the curve has to be 1. The area under each side, since it's symmetric, that means half the data is below the mean and half the the data would be above the mean. And finally, if it's bell-shaped, we could use the empirical rule. So remember on your formula sheet it tells you, and I put the empirical rule back on here in case you'd forgotten. It tells us that 68% of our data was within 1 standard deviation of the mean, 95% within 2, 99.7 within 3. So normal data is nice, pretty data where everything works like we want it to. There's no skewedness, no outliers, nothing like that. So far, so good? Alright. Wouldn't be fun if I didn't give you a big, nasty set of data. So, we haven't done this in a while. Let's take a bunch of numbers here. This data tells me the heights of a random sample of 52-year-old males. I want a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. It's been a while since we've done this, hasn't it? We've done them on our calculator. We can just as easily do it on here, just do it by hand if we're drawing our histogram, so it's really not going to be a big deal either way. But when we do this, I am asking for, I did give you some stipulations here. The first class is 31.5. So, and the class width is 1, so where does the next class start? 32.5. Okay. Remember the first class would have to end right before that, so it would go to 31.4. Next one would go from 32.5 to 32.4, and so on. Let's do, it's really not going to matter if we do a relative frequency or just the frequency. Did I put these in numerical order for you? Oh, I did. That is really nice. You don't even have to sort through them and find them. Since I already put them in order, let's just do it by hand, since it won't be too hard. Okay, so my first class will go from 31.5 to 31.4. So how many points fall within that? 1. If I were going to plot the relative frequency, remember frequency versus relative frequency, it doesn't matter. The only thing that changes is your height. Or, sorry, not your height, your labels here. If you were doing frequency, you would call it with just a 1. If I said relative frequency, what would you have to do? Divide it by how many do we have? 50. So if you take 1 over 50, what do you get? 2. Alright. So let's go to when we draw this, my rectangle would start at 31.5. The next one will be at 32.5, so it would stop here. So it would just look like that. Alright, next one would go from 32.5 to 33.5. How many do we have in that window? And it would have to stop right before the 33.5, right? So that gives me 3 in that window, which is 0.06. 3 out of 50. So the next one would have to go from 33.5 to 34.4. So we have 6. So that is, what's my probability there? 6 out of 50, so 0.12. Did I everybody understand where I'm getting my numbers? Helps if you can draw straight lines. Okay, so this would go from 34.5 to 35.4. So we've got 10 out of 50. So that would be 0.2. Next one would go from 35.5 to 36.4. So that one has 11.22. So from 36.5 to 37.4, we get 10 again, so that's 0.22. Sorry, 10 again, so 0.2. From 37.5 to 38.4, we get 5, so that's 0.1. From 38.5 to 39.4, we get 3, so that's 0.6. And you would end at 40.5, and we only have 1 in that window, so 0.02. So that was the histogram, assuming all my rectangles were straight. So does everybody understand how we got that? And like I said, you could do it on your calculator. It just wasn't that hard to do it by hand. I figured it wouldn't hurt us to kind of review where those things are coming from. Then I asked you the question, do you think this is normally distributed? Yeah, we see the middle is definitely the highest, and it's symmetric on both sides. Those rectangles are the same height as we go all the way out. So yes, this one is normal. Okay, just a couple more examples and I'm done. Couple things when I'm talking about this, there's a couple homework questions that'll say, give 2 interpretations. So this is the slide you need to look at when you do this. Area under a normal curve, we can interpret it 2 ways. It's the proportion of the population with the given characteristic. So it could be, the percentage of the 2-year-old boys that had a given height. Or it is a probability. So we could say, there's a 30% chance of this happening, or we could say 30% of the population had this characteristic. So we can look at it just describing the population or as a probability. So let's do that here. The weights of giraffes are approximately normally distributed with a mean 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. Okay, if I ask you to draw a normal curve, you're drawing me a nice bell-shaped curve. Where is my center? It's the mean, which was 2,200. Then these points, my inflection points here, have to represent my standard deviation. My standard deviation was 200, so that means 200 above and 200 below. So 200 above this is 2,400, 200 below it is 2,000. All right. Part B, shade the area under the normal curve to the left of 2,100 pounds. So 2100 would fall in between these two, right? To the left. This is kind of leading us into what we're going to be doing in section 2 of this chapter. We'll be finding those actual areas under that curve. So part C says, suppose that this area is 0.3085. Provide two interpretations. So the first thing we could say, if you look back at those options, first one is talking about the proportion of the population. So I could say the proportion of giraffes and this is 2100 and to the left, so that would be less than. So weighing less than 2100 pounds is 0.3085. The other interpretation is a probability. So the probability a given giraffe weighs less than 2100 pounds is 0.3085. So we're either looking at it as the probability that something could happen, or looking at the giraffes that I have describing how their weights are distributed. And then the last thing I wanted to do was look at a couple questions, kind of like your homework, and just make sure we knew how to do this. So if you could get out your book, we're going to do 23 and 25 together. Page 360. Okay, so this one says, one graph in the figure represents a normal distribution that has a mean of 10 and a standard deviation of 3. The other has a mean of 10 and a standard deviation of 2. So we need to look at these graphs A and B and decide which is which. So they have the same mean. Okay, the bigger your standard deviation, what will that do to your curve? It'll spread it out, because if the bigger your standard deviation is, the further you have to go from the center before it starts to flatten out. So the one that is more squished in would have to have a smaller standard deviation. So which one has a standard deviation of 3? Which one's more spread out? B. So the standard deviation of 2 would have to be A, because it is a skinnier one. Alright, problem 25. We did one kind of like this already. I did it as my example, but can you look at that one and tell me the mean and the standard deviation? Mean is 2. The mean is your center, your peak. Standard deviation is from that point to the inflection point, when our graph kind of starts to curve out. So that would happen after how far? 3. We okay reading this? Okay, knows what I got?